So we saw a couple of prerequisites and we are all set to go ahead and then make our required observations. Let us go very slowly. I'll help you all recollect what has happened so far and then try to connect different pieces of the puzzle. So, what does one observe of this matrix multiplication process? Right? So we observe that no matter what vector we choose, irrespective of what vector we choose, remember the screencast that I did of the Python programming code? I took different vectors. No matter what vector I chose, I landed up with the same vector, right? We all converged. We observed that every single vector, no matter where you start from, repeated application of the matrix results in the very same vector. By very same vector, I mean the same direction, right? This we observe. Why did this happen? What makes this process of applying the matrix repeatedly on a vector and scaling it down, of course. Scaling it down is to ensure that the numbers don't become big, that's all, nothing else. As you keep applying the matrix on any given random vector, it always goes to the same point in R2 plane. R2 is that two-dimensional plane, correct? Why is this happening? What is the physics behind it? What is the logic behind it? And let us unravel that slowly. So, let us recollect some basics from our, again, high school mathematics. Throughout our discussion, we are not going to use anything hi-fi. All we are going to use is some very basic matrix theory. I'm sure you all have heard of eigenvalues and eigenvectors, right? So, let us recollect that. So, given a matrix, we know there is something called an eigenvector and an eigenvalue. What is that? Let me help you recollect it. An eigenvector is something of a matrix A. Eigenvector V is defined as something that simply gets scaled up by a lambda factor. Then lambda is called an eigenvalue and the V is called an eigenvector. Correct? Okay. So this is the right time for you to open, let's say, Wikipedia or any other online reference and then refresh your basics of eigenvalues and eigenvectors. You only need this definition that A of V is equal to lambda V. This is the first thing that you need to know. And second thing that you need to know is for a 2 cross 2 matrix, let's say A, 2 cross 2 matrix A, there are two eigenvectors. Not always, but mostly you will always have two eigenvectors. Okay? And these eigenvectors are independent. They are independent. What do I mean by that? By that I mean you take any vector of your choice. Let's say any vector Z. You can always write Z as a linear combination of V1 plus some beta times V2. Because that they are what is called linearly independent, you can always write any vector as the linear combination of V1 and V2. If you don't know these things, you probably should brush up your basics. So this is the third one. First one is the definition of eigenvalues and eigenvectors. Second one is given 2 cross 2 matrix, there is always two eigenvectors and they're actually linearly independent. What do you mean by linearly independent? Two vectors that are linearly independent in R2, given any point in R2, that point can be written as the linear combination of these two eigenvectors. So this point is Z. You can always write Z as alpha times V1 and beta times V2. This is the basics of matrix theory. I'm sure all of you are familiar. If not, please take a pause and take a look at it. You needn't know the reasoning behind all these things. You just need to recollect these things. That should be enough. Okay, so let's go further now. Okay, so please revise them before going any further. You should know what are eigenvectors and eigenvalues. I'm not going to apply them in any not so obvious manner. Every single application of this concept will be pretty straightforward. So I hope you have recollected what is eigenvector and what is an eigenvalue, and I proceed further. Okay. The how and why of eigenvectors and eigenvalues here. So what did we do in our programming screencast? What did we observe of this matrix multiplication? Whenever a matrix A acts on any vector V, please observe that A is a matrix, V is some random vector V, then you can always write V as a linear combination of lambda 1 times V1 plus lambda 2 times V2. This is always possible, right? We just now saw in our previous prerequisite. This is always possible. Let us note this. Okay, next. So this V1, V2 are eigenvectors and lambda 1, lambda 2 are eigenvalues. We observed it already. Okay, I'm just helping you recollect it by saying it once more. Okay, so far so good. So all I'm saying here is any given vector V, if a matrix A is applied on it, then you can always see it as A being applied on a linear combination of eigenvectors V1 and V2, no matter what V you choose. Now what is this equal to? This is equal to A is a matrix, its application on a scalar lambda 1 times a vector V1. You can always pull out the scalar here, as you can see. You can pull out the scalar here, correct? So you can write it as lambda 1 A times V1 and lambda 2 A times V2. But then observe carefully, what are V1 and V2? V1 and V2 are eigenvectors. And so what if they are eigenvectors? If they are eigenvectors, you can further write this A of V1 as lambda 1 times V1. Right? A of V1 is lambda 1 times V1, A of V2 is lambda 2 times V2, and you finally get this. Correct? Okay. As I continue this process, look at my previous slide. As I continue this process, I apply A again on this. I continue to apply A again on this. What do I get? I repeatedly apply A. Okay? That is equivalent to me applying A k times on V. So I'm talking a lot of things sort of very quickly. I suggest that you take a pause and then take a look at what I'm saying. Okay? Alright. So I'm applying A k times on V, which gives me lambda 1 to the k times V1. Why? Pretty obvious. Look at the previous slide. If you're confused, look at this. Understand this carefully and you'll understand what I'm doing here. This gives me lambda 1 to the k times V1 plus lambda 2 to the k times V2. Correct? Perfect. So far so good. Absolutely no confusion so far. Right? Observe carefully. This lambda 1, let me assume, is greater than lambda 2. Alright? This always holds good. Eigenvalues are most of the times distinct. When they are distinct, one of them is greater than the other one. So when one of them is greater than the other one, what happens? Lambda 1 is basically the amplitude. Right? Lambda 1 to the power of k, if lambda 1 is some, let's say 2, a number greater than 1, then lambda 1 to the power of k for a huge k will be a huge value. Right? This is what we call as amplitude for the vector V1. When you multiply lambda 1 to the k to V1, it sort of scales V1 up. Lambda 1 to the k being a big number, when multiplied to a vector V1, it just makes this vector shoot away from origin, right? We have discussed this already. So think about it for a minute. V1 simply signifies the direction, and this product tells us the final vector, which is extremely scaled, right? The value, the existing V1 is getting pushed by this value lambda 1 to the k. That's what this means. Okay. Let us note something here. Let us observe this carefully. Let us take these two numbers 2 and 3. Right? Just plain simple 2, number 2, number 3. And look at this. 3 is 1 more than 2. Correct? As simple as that. 3 is 1 more than 2. Right? Which is like saying 3 is 50% more than 2. Correct? But then when you square it, 2 square gives you 4. 3 square gives you 9, and then what happens? This 9 is more than twice of 4. When you take two numbers a and b, if B is greater than A, if you look at their proportion by what factor it is greater, you observe that this number is 50% greater than this number. But when you square them, you observe that it turns out to be twice as much as this number. As you continue this way, you will observe that, look at this, what happened. If you cube it, you get 8 and 27. Now that's surprisingly more than 3 times. So this is like saying, let me give you a very nice fictitious example. Look at your bank balance, look at my bank balance. Assume your bank balance is 2 lakhs and my bank balance is 3 lakhs. Let me make you feel happy by making you rich. Assume your bank balance is 3 lakhs and my bank balance is 2 lakhs. Alright? Which is like you are just 1 lakh richer than me. So assume God comes and cubes our bank balance. He cubes. So my bank balance was 2, he makes it 2 cube, and your bank balance was 3 lakhs, he makes it 3 cube. So initially you were just 50% richer than me, but now you have become more than thrice richer than me, right? So this, although God came and cubed me as well as you, he gave the same gift both to me and you. Depending upon what was the number that we had, we ended up having a bigger number. A person who had more now has a lot more. I think you got the intuition. So now, as we keep going on further, this was more than thrice, we observed. We keep doing this. Let's say we empower it by 100. Then we observe something really startling. This 3 to the 100 is several folds bigger than 2 to the 100. So big that, let's observe what happens. So big, it's several folds big, that so much more than this, that if you look at the ratio, it is close to 0. Why? 2 to the 100 divided by 3 to the 100, as you can see, is 2 by 3 whole to the power of 100. 2 by 3 is a number smaller than 1, and you are empowering it to the number 100, which is a very big number. You take a number less than 1 and keep multiplying it to itself, it will quickly go to 0, you see. That's what's happening here. Take a minute's pause and observe what exactly we explained in this slide. Look at the previous slide. Right, we are talking about the multiplication of a big number, namely lambda 1 to the k to v1, and lambda 1 is greater than lambda 2. What is the connection between this and what we discussed here? What is the connection between this slide and this slide? Take a minute. I repeat, stare at this slide, see what's happening here. Stare at this slide. What did we just now say? And collectively we can say something in the next slide. This is the right time to pause and think about and guarantee yourself that you understand this slide as well as this slide. Now let's go to the next slide if you are through with these 2 slides. It is so big that the ratio is 0, we saw that, which implies that 3 to the 100 is several folds bigger than 2 to the 100. I'm just stating the same thing repeatedly. So what? So we can make a big inference now. We observe that when you empower A, when you repeatedly apply A on any random vector V, you can always write this as lambda 1 to the k v1 plus lambda 2 to the k v2. What happens? This is amplitude and this is the direction. We discussed that. Lambda 1 is greater than lambda 2, which implies lambda 1 to the k is way greater than lambda 2 to the k if k is big. We saw 2 and 3 example and k was 100. It was huge, so much that the bigger one simply completely dominates over the smaller one, so much that the smaller one is negligible in front of the bigger one, so much so that the ratio goes to 0. Correct? Okay. So now this implies that A to the k of V is lambda 1 to the k v1, which is a very big quantity. Why? That's because lambda 1 is greater than lambda 2, and this results in lambda 1 to the k being very greater than lambda 2 to the k. This is a bigger entity, this is too big, this is small compared to what? Small in comparison to the big thing that's sitting here. And I'm sorry, it is not the V1 which is big, it is this entire thing that is big, is what I mean here when I say big. This entire thing is small in amplitude is all I'm saying. Okay, let's go next. So we saw that A to the k of V is so much, and this one is really huge, this one is really small. When I say really small, it's comparatively small. right? Okay. So now when you take a big vector and add it to the small vector, what do you get? Do you recollect? Do you see the bells ring in your mind? We saw a prerequisite, right? We saw that whenever a big vector is added to a small vector, it will simply be in the direction of the bigger vector, right? Which means my a to the k of v will result in lambda 1 to the k of v1, and you can simply ignore this factor here. Okay, perfect. So what do we conclude? We conclude it's in the direction of v1, and please note this v was a random vector. Let me write that down. This is the most important observation. It was a random vector, and no matter what you chose for v, no matter what you chose for v, it was a random vector. No matter what we chose for v, you always ended up with v1. What is v1? v1 is the eigenvector corresponding to the highest eigenvalue. If lambda 1 is greater than lambda 2, then I take that corresponding eigenvector, and this is independent of this v, and it is something to do with the matrix that you take. So whatever vector you take, you always end up with the eigenvector. Do you see why? I just gave the explanation. Again, this is the right time to pause and then understand what I just now said, and that completes the proof for the fact that whenever you take a matrix, our screencast, if you can recollect, we did a screencast of our programming where we took a matrix 1, 2, 3, 4 and applied it on different vectors. It was going to the same vector. Why? This is the reason.